Hello, everyone. Welcome back to our AP Physics, A-Level Physics, IB Physics series. My name's Andrew, and I'm here to try and help you out by providing some information about things that you're studying in your kinematics physics courses. And today, we're diving into a central concept, the conservation of mechanical energy, whether we're thinking about a roller coaster ride, whether we're thinking about pendulum swinging, whether we're thinking about going up and down half pipes. Understanding mechanical energy conservation is crucial for analyzing the behavior of these objects in motion, right? But what exactly is mechanical energy? What are the components of it? And how does it remain constant in certain situations? Like this situation I have here of this roller coaster car going up and going down. Based on these graphs here, I'm actually seeing a conservation of the mechanical energy. So let's dive into the intricacies of that. So mechanical energy, as we can see in this first line here, is the sum of the kinetic energy. Let me just highlight these things, right? Is the sum of the kinetic energy, the energy of motion, and potential energy, the energy stored in an object due to its position or state. In this case, relative to its position in a gravitational field, right? So according to the principle of conservation of mechanical energy, in the absence of non-conservation forces like frictional forces, air resistance, drag, right, the total mechanical energy of the system remains constant. So it remains equal to the sum of the kinetic and the potential. And here we can see the kinetic energy and potential, actually written out, right? The potential energy being a product of the mass of the object in question, the gravitational field it's in, and the height, its position within that gravitational field, right? You raise something to a higher height in the gravitational field, and it has a larger potential energy store. And then we've got, of course, our kinetic energy equation, right? Half mv squared, right? The mass of the object, the square of its average velocity. Okay. So, for instance, let's consider something here like a pendulum swinging backwards and forwards. So it starts here, it goes here, it goes up to here, and then it goes backwards and forwards. All right. As it reaches its highest point, all right, all of its energy is being stored as the potential energy. All right. And at its lowest point in the swing, it's all kinetic. All right. That's when it's at its fastest. Yeah. So we had high GPE here. That GP is transferring. Remember back to conservation of energy. Energy is not created or destroyed, it's just simply transferred, right? So that GP is transferred to kinetic. That kinetic works to transfer back to GPE as it rises in height and position in the field, yeah? Remember, potential energy is due to its position in the field, right? And then it goes back to kinetic, right? So at the black point, it's at its highest velocity because we've got max Ka. At this point here, it's the transparent. We have 0 Ka as it stops and changes direction, and that mechanical is purely as potential. And we go backwards and forwards as I'm kind of scribbling with this little yellow. All right. So throughout the entire motion, the sum of the kinetic and the sum of the potential remains constant. That GP transfers fully to Ke, that Ke transfers fully to back to GPE. So that sum number, that mechanical number, is staying the same as long as we are not accounting for and we are ignoring the non-conservational forces at play, right? If we're just ignoring friction, we're ignoring drag, which in reality on Earth do exist. So in reality, that isn't going to be conserved. It's going to suffer dampening and eventually stop, right? But ignoring those forces, perfect, 100% efficiency. Now, when solving problems involving conservation of mechanical energy, we need to remember to identify all forms of the energy present. All right, so we have to take in that realism, like I said there, right? Account for non-conservation forces and apply the principle that the total mechanical energy remains unchanged. All right, so you need to like say, oh, okay, I've done this, but however, there are these non-conservational forces, so there is going to be, some energy that is transferred inefficiently, that isn't transferred to the kinetic because that's transferred to friction. Whether that's friction due to the air or that's friction due to like the chain at the top of here or whatever. But, so whether you're analyzing the motion of a roller coaster or a simple pendulum, understanding and applying the conservation of mechanical energy is essential for your AP physics courses, your A-level physics courses, your IB physics courses, right? Let's kind of mess around with that a little bit before we finish off. Yeah, let's see if my pen's penning. It is. So, I'm somebody who skateboards. So let's just go with a little half pipe, a little mini ramp problem. Okay? Applying this conservation, right? We can solve and find out what my maximum velocity might be in the middle of the mini ramp. Yeah, it's really, really simple to do because we know that KE and that potential energy are equivalent to each other. I know that all that GPE transfers to the KE. If I'm just going to ignore and simplify by not taking account the non-conservational forces, which of course exist, all right, because I'm going to be suffering drag on my body, from the air resistance, and there's also going to be drag and friction from the wheels, the trucks, in contact with the wood of the half pipe. So it's not this idealized, but let's just say as is. So I just start substituting in the equations. Half mv squared equals GPA, which is mgh. All right, and what can we start to do here? Well, we can simply just start to substitute in values which are relevant to the situation. All right? Oh, cool. Because we said let's work out how fast I was going. Let's work out my velocity. Let's clear up a little space here. I'm going to get a better pen for future videos because this is a little bit clunky, isn't it? Okay, so let's just rearrange this using some simple algebra. So I'm just going to do one step at a time. I'm going to bring that half to the other side. So multiply each side by 2gh. Okay, great. The mass in question is the mass of me. So it's the same mass on each side. I'm just going to divide each side by my mass and simplify it to v squared equals gh. Cool. So v is root gh. Okay, so substitute in the value for g for Earth. Let's put in 9.81 meters per second, 9.81 meters per second squared, 9.81 newtons per kilogram, however you want to say it, whichever one lets you conceptualize what a gravitational field is best. I mean, go wild. And then substituting the height that I've displaced, the vertical height I've displaced in the field. So let's say that's like, I don't know, a 1.5 meter half pipe. Yeah? So what am I doing? 9.81 multiplied by 1.5, square root. Boom, I've got my max velocity for when I'm in the middle. So how you can actually sort of apply those to, a really, really simple situation like this, to find unknowns, find, velocities, you could do the converse, right? We could be going like, oh, I know I can get to this velocity. How high is that going to take me? Yeah, so I could be substituting in the V for a solution to find H, just kind of stuff like that. But there we go. A little introduction, a little discussion about mechanical energy. As always, if there's things you want to talk about here, you just shout out in the comments or whatever. I've got all my contact details in the bio on the channel, in the description below. We're on Instagram, we're on Twitter, we're on all these places. You can buy resources or get free resources from me on TESS, my TESS storefront. All this stuff is in the description below. If you're interested in other things here, you're interested in private tuition, you just get in touch and we can help you for your AP, A-level, IB, GCSE, whatever the hell physics needs. But there we go. Bye-bye, everybody.